All right, well, it's time for us to get started with our review. I don't really have any plan for that, so I'm hoping that you all do. How can I be useful today in our preparations for tomorrow? Yeah.
I found I didn't have much written down about this. What exactly is the difference between like iteration and recursion? Could you like?
Yeah.
Like, I know, but I couldn't put it in the words.
I would, if something like this appeared on an exam, I would say that there is no difference between the problems that they can solve. Anything you can solve iteratively, you can solve recursively, and vice versa. But the reason we learn both is because some problems are very naturally easier iteratively and very naturally easier recursively. And if you were asked to give an example of this, iteratively, I don't think I really gave great examples of it. The easier recursively would be like the towers of Hanoi that we saw. We saw a recursive version that required a stack and it's got 100 lines of code. And the recursive version was just a few lines of code. And granted, the intellectual thought behind the recursive solution was in depth and difficult to understand. But if we had perfect understanding and a lot of experience with everything, then if somebody asked you to implement a solution to the towers of Hanoi, you should choose recursively because you'll be done significantly faster. That's what I was hoping to get out of the difference between iterative and recursive solutions to problems. So there's no difference until it matters. What else?
Would you ask this question that's that complex, like the towers of Hanoi?
I would not have you solve the towers of Hanoi problem.
Are we gonna have to do any polls for that or something?
Possibly, that is something that could show up. I did hint yesterday that there is at least one code-related problem, and on the study guide, it says that it is not related to stacks. So somewhere in there, either in sorts or in recursion, there will be some code-based problem.
So similar to the other one, there's one code question.
One or the other of those. There's either one or two implementation options. I wouldn't put more than two on. But there might be up to two.
Did you give us a code example and like we have to write the runtime?
Maybe. I did mostly cover targeting runtime on the last exam. So probably not something that's exactly like that, but I might ask you to explain the logic behind the runtime of some of the algorithms that we have covered. So we talked about the sorts, so you should know the associated runtimes of the sorts that we've covered. In the best case, the average case, the worst case. You should be able to explain what that means intuitively, not just memorize the order, but be able to say, what does that mean?
Can we go over that?
Yeah. So what do we want to use as an example? Someone give me a sort and give me a best case, average case, or worst case.
Insertion sort.
Insertion sort, best case, average case, worst case. Average case of insertion sort. Let's see if we can figure that out. So someone described to me at a high level, how does insertion sort work?
Start at the first index or like the start at 0 and you compare your previous. And then you continue if it's the correct order to swap. Something like that.
I think that's more of a bubble sort than insertion.
Okay.
sort. We're gonna be swapping each one backwards into place. So we know that the first element is sorted with respect to itself. So we start looking at the second element, and we're going to compare, is this second element less than the element that came before it? Since we know that everything before it is sorted, we just have to move it back into place. So we may be doing one swap here, or we may not. Once we complete that, we know that the first two elements of the array are sorted. So we start looking at this element, and we now say, let's move this back into place. So we're gonna compare it with this, until we find the place that it should swap. There should only be a single swap associated with this. You're not gonna swap it a bunch of times, because there's no reason to do that really. Or is there? How do we ensure that the list is sorted? Do we swap once? Do we swap a bunch of times? We do need to swap a bunch of times. So let's say we have something like, we know this is sorted, so 3, 4, and we find a 2. No single swap is going to keep this in order. We need to have 2 swaps for this. So we identify that this comes first, but if we wait to swap until the end, then we end up with 2, 4, 3, which is still not in order. So we need to compare swap. Pair swap. Now we're back at the beginning and it's in order. And now we know that this much of the array is in order. So now we can look at this element and move that back. So if we wanted to figure out the average case analysis of this and be able to explain it, what should we note or how should we go about that?
Well, it's dependent on the size of this.
It's definitely dependent on the size of the list, so we're gonna call that variable n. However long this list is, there are n elements in this list. So first of all, how many times are we comparing? Are we inserting something into an already sorted list, sublist? So the first time we looked at this element, then we looked at this element. How many times are we looking at an element and inserting it into place? N minus 1. In this case, it's 4 because n is 5, but we want to talk generally because we want to come up with some kind of general average case expression. So I'm going to call this the outer loop. For each one of these, how many times are we on average swapping it before it's in place? We can assume it's going back about halfway on average between its current position and the beginning of the list. So when we look at this element, how many comparisons are we making? 1, regardless of whether we swap it or not, we need to make a comparison. So here we have 1. Here, we either have 1 or 2. So an average for that is something like 1.5. Here we either have 1 or 2 or 3. So an average for that is 2. And we will start to see that the pattern continues regardless of how far up we go. You could also think of this entire sequence as something like, if we wanted to kind of double this is like 3, 2, 3, 4, 5. So it's the 1 plus 2 plus 3 plus 4 plus 5 over 2. And that's the average that we are doing. But since we're only going back halfway, so the inner loop is something like we're doing n over 2, n over 4, and either way there it's going to end up being the same order. So we have about n over 2 operations to do in the inner loop for each of n minus 1 times. So if you wanted to expand this, whenever we have a loop inside of a loop, we multiply. So we should do something like we have the quantity n minus one times n over two. What does that come out to?
There, divide by 2 minus 10 divided by 2?
Yeah. That would work. So if we wanted to just be able to add them together, we have to get this over two as well. So you multiply by two, divide by two, and then move over, so you get something like n squared minus n over two. What order is this in?
How about n squared?
It's in n squared. This is a constant, so we can ignore it. This is a less order, so we can ignore it. So this is in big O of n squared. So the average case for this is quadratic. What does that mean? If you were to interpret, all right, the average case of this is quadratic, what does that mean? So we did an average case analysis for this, but yeah, the big O says that the average case may end up in a better order than this. We didn't really prove that, but the average case is at worst n squared. Further looking at this, what does that mean in terms of the complexity of sorting a list? If you were to state that in English and not computer science speak.
Really say the larger the list, the longer it's gonna take.
Yeah, we would say something like as the list grows, something like that. As the list grows, the time required to sort it grows proportional to its square. So the square of the size of the list. We don't know that it grows exactly like that because we talked about an order and we got rid of a lower order and a constant as we do this, but we know it grows proportional to that. Which means that there may be some lower order terms and there may be some constants, but the proportionality is consistent. So this would be a good English interpretation of this map and this idea.
So the best case would just be O then. For that, or
Would it? Let's go through that logic. How do you arrive at the best case being n?
sizes.
Well, we don't care. The best case is proportional to itself as well.
Best case is either putting it in, it's in order.
Yeah, yes, that is the reason that it is linear. So if this list were to be sorted already, so we have 1, 2, 3, 4, 5, etc. It could also be sorted in any other way. When we look at this element, how many swaps do we need to do? We have 1 comparison, 0 swaps. When we look at this element, how much work do we need to do? 1 comparison, no swaps. For each element, it's always exactly 1 comparison and exactly 0 swaps, which for each element is constant. So for n elements, it's going to take time proportional to that size. If there are a million elements, we're going to do one comparison and zero swaps 1 million times. So that's why it's linear in terms of the size of the list. We don't want to say the best case is the list is of size 0. We want to think about the underlying structure of the data with proportion to its size. The best case for your next homework assignment is that it's easy, not that I don't give it to you.
I like this example. Can we go through all of them? That's okay. Since we have time.
All of the other sorts.
Just like a quick, overview.
Yeah,
There.
we could do that. Does anyone else have any other points they'd like to hit from that? I'd like to do kind of a cursory hit of everything until we've done that, and then we can absolutely go back through as many others. Yeah. Yeah, a recurrence relation was the concept of how long it takes for, it's kind of the complexity analysis for a recursion problem. So we said that we were going to have some recursion problem of size n. So that tells us that we have some expression t of n. This is the time it takes for a problem of size n. And we're going to write this expression in terms of how many subproblems there are, as well as how complicated it is to put together a solution once the subproblem returns with its solution. So the example of the number of people in front of you in a line, we said the complexity of a problem of size n is we have to solve the problem of size n minus 1. Right? The person ahead of you needs to figure out how many people are ahead of them, which is some amount of work that we don't really have the ability to look at yet. And then how complicated is it to figure out how many people are in front of you, given that we know how many people are in front of the person in front of you? You need one operation, you just need to add 1 to it. So we have a recurrence relation that looks something like this, where this is the complexity of this problem. This is the problem of the complexity of the recursive problem. And the size of the recursive problem. And then this is the, I don't want to call it. Look at this here. We also, when we do this, need the complexity of the base case. So you also need to say something like T of what is the size of the problem that we can immediately solve in terms of the number of people in front of you. 1, if you're the first person in line. If you're the first person in line, there are 0 people in front of you, which takes you constant time to figure out. You return it, you're done. So now we have the ability with just this base case and this recursive case to figure this out for any problem of size n. If we wanted to figure out the size of t of 2, we could write this by saying 2 is not equal to 1, so we have to use this t of n. So t of 2 is going to be t of n minus 1. But t of 1 is equal to 1. So we can solve this recursively and come up with a time for it. So now we have kind of this as a lookup in a table somewhere. T of 2 is equal to 2. So now how do we solve t of 3? This isn't 1, this isn't in our lookup table. So when I'm using this lookup table example, I'm actually using an advanced algorithmic technique called dynamic programming. You'll see it in, so we don't usually do this. We still have to go all the way down the recursive chain and back up when we're analyzing this. But an advanced technique kind of lets us store these results as we go in a table. I think that it makes it make more intuitive sense anyway. So this is equivalent to a t of n. We don't have a solution for this. So this is equal to T of 2 plus 1. We know from our lookup that T of 2 is 2, so this is 2 plus 1. And we start to see that we have a pattern emerging as we figure out the complexity in this recursive solution. And this tells us that, in fact, the T of n is in big O, and in fact, we can show from this is actually in big theta, it's exactly in order n. As n grows, the amount of work that we need to grow or do grows exactly proportionally to that. It's not in any other order.
What was the plus one again?
This is the amount of work that it takes. Once the person turns back around and says, there are 84 people in front of me, you go, plus 1. There are 85 people in front of me. It's the number of operations that you need to put it together. So now that we've seen merge sort, we could construct something like this for merge sort. So I will just spoil right now that I'm not actually gonna have you solve any of these because I didn't assign anything like this. I just wanted to introduce you to the idea. You will be solving recurrence relations in algorithms, CSCD 320. But I feel like if the idea is in your brain and you go to see it, then it will make more sense. I do want you to have an intuitive idea of what this is. So if I asked you, what are the components of a recurrence relation? I would expect you to be able to tell me that we have the complexity of this problem, the complexity of the recursive problems, and how complicated it is to solve this problem given the solution to the recursive solution. Sometimes we have more complicated recursive problems. So merge sort is an example of something that's a little bit more complicated. So in merge sort, how many recursive calls do we have? Yeah, we need to sort the left half and sort the right half. So we have the complexity of something plus the complexity of something plus the cost of putting it back together. Now, the question that I have is, what is the size of the problems that we are trying to solve here? Half of the original. So we're breaking this down to T of n over 2 plus T of n over 2 plus what is the complexity of the merge? This is the merge procedure that we have to do. Once we have these sorted left and right halves, we actually need to construct the new sorted list. It is constant. We have n things to do. So this would be a recurrence relation for merge sort. How complicated is it to solve a problem of size 1? Because we need a base case here as well. So we know our base case is a list of size 1. How complicated is that? First of all, do we make any recursive calls? How many operations does it take for us to be ready to return with a sorted list when we have a list of size 1? We just return. So that's our base case. So now if we wanted to solve a problem of size 2, for instance, we're going to make a substitution for n equals 2. We can do something like T of 2 equals, what is 2 divided by 2? T of 1 plus T of 1 plus a substitution for n. So given this stored in the table, we can calculate T of 3, T of 4, T of 5, etc. But it turns out that if we were to solve this and map it onto a function, we would see if this is you would end up with n log n. The order of n log n. This complexity would be log n. This complexity would be log n. This complexity is still n. But it's n times the log of n. So when we break this down, we have log n times this n. Since we're going to be breaking this down into half. So we're going to do this merge procedure log n times, which creates this order. So this isn't as much review as it is just hopefully just making recurrence relations make more intuitive sense. So please don't feel the need to memorize this entire procedure. I'm not going to ask you to do it. But if I did ask you to intuitively explain this concept, maybe this helps you to better intuitively understand.
Called stacks.
Yeah.
You asked me able to reason about how to stack and information, like specifically.
Yeah, so if I told you that we have a stack, and then I said, we're going to push 7, push 3, pop, push 8. P. What does the stack look like at the end of that? So just having an understanding of what push does, what pop does. I'm not gonna have you write any code for it, but I expect you, if I were to say, here is a call to a stack and some operations, what happens? As well, I may ask you to do things like analyze how a stack solves a postfix expression. So I might ask you for the associated stack calls if we had a particular postfix. So if we have, I'll use a really basic example, like 2, 3 plus. I would want you to be able to identify as we go through the symbols, what is the stack doing? So when we read 2, the 2 is a push. When we read the 3 is a push. When we read the plus, this is a pop, an add, and a push. And then if I ask you to draw the stack contents for each one of these, you would see that we have a stack with 2 on it, we have a stack with 2 and 3 on it, and we have a stack with 5 on it at the end of each one of these operations. So something like this kind of work for a more complicated postfix.
That was a minus, so it would be 2 minus 3.
Right. If this were a minus, then when we pop into the second position before we pop into the first position. So if we're thinking of this like this, this, where the op stands for operation, this is the top of the stack. Goes to the second position. So we would get 3 here and 2 here. And it's because we read left to right. That's the only reason we do this. Since we read left to right, we expect this to be 2 minus 3. And what's going to be on top of the stack is the thing that was added most recently, which is the thing on the right. Which is why we have to kind of invert that and pop to the right instead of pop to the left. Other questions? We want to go back to the sorts and sort analysis.
When you talk about that images, that's just what you're talking about, like when we do the.
Yeah, it's being able to, if you can express what's happening. So for each one of these sorts, maybe have an understanding of what's happening in the process. My goal when I design these exams is regardless of what you put on your sheet of notes, you're going to have to interpret that in some capacity. You're not necessarily, for most of the exam, going to be able to look at your sheet of notes and the answer is going to be there. Otherwise, I wouldn't give you a sheet of notes. I want that to be the assistance that helps you to be able to interpret the algorithm. So have a good understanding of how these algorithms work, kind of on a line by line basis. What is actually happening at a visual level? How is it sorting it visually, not just the beginning and the end, but at the midpoints in this algorithm, what is the internal state of the memory? What are the internal states of the arrays? Where are the counting variables? Where are they pointed? What's going on? So know that level of detail on each of these sorts.
And merge sort won't be in.
Correct. Only the three basic sorts. Insertion, selection, bubble. Optimized bubble.
Bubble sort. I understand optimized bubble, but I don't really understand the normal bubble.
Yeah, so the only difference is that optimized bubble is stopping once it's not possible to make any more swaps. Because after the first iteration of bubble, we've bubbled the largest value to the top. We've made some other changes throughout the array, but we know that that maximum element is there. Once we've done this 4 or 5 times, the 4 or 5 largest values are there. And in fact, there may even be some other ones that are there. We can actually stop once we recognize we didn't make a swap. If we didn't make a swap, that means that we're not carrying the largest value with us anymore. The next largest value is in place, in which case we don't need to continue moving throughout the array. We can just kind of stop there and also bring a pointer back to our current position that says, we don't need to worry about the rest of this, it's already sorted. So the non-optimized version is still making all of those comparisons unnecessarily. It does not change the order of the runtime. It doesn't change the best case, the average case, or the worst case at all. But it still saves us a constant amount of time. You know, may shave off 1/4 of the runtime on average. It doesn't change the order, but it still runs faster. But it is making unnecessary comparisons because intellectually we know that everything that comes after that is already sorted. So we find those kinds of small optimizations a lot in computer science. Nobody cares too much about them. They're enough to mention, but they're not world-shattering breakthroughs. World-shattering breakthroughs change the associated orders of the best case, the average case, or the worst case. There you go. We have a new way of solving this problem more efficiently as it scales.
Where's the first counter or pointer going on the insertion sort? Is it going on the second element, or I guess the?
Yeah, we already know the first element is already sorted. So we
it's gonna
don't even
get-
start.
So it's gonna get the second index, or I guess the first index, and then check it with the one behind it.
Yeah, index 1, we're gonna start checking. Index 0, we know is already sorted with proportion to itself. With respect to itself.
Oh, okay. And then it'll check one behind, check one behind, check one
Yeah.
behind. Okay.
Yeah. So this outer loop starts at index 1, not index 0. This is important.
But it just moves forward while checking the one that's behind it.
Yeah, checking the ones. It'll continue to check until it swaps it back into place. If we were to give like a 1-sentence overview of insertion sort, I would say it's something like, for each position, starting with the first, which is really the second, swap it with previous elements until it is in place. You're just swapping each element, taking this element, swapping it back into place, this element back into place, this element back into place, which means that you're continuing to grow the sorted part of the array.
How much detail are you looking for like pseudocode if we write that, like for concerning, for example, do you want us to go pretty deep detail, like similar to if we were writing it in Java? Or
Probably,
just walk through the steps, that kind of.
yeah, I'm looking for more so than can you copy, because we have the code on the slides, right? So if you're thinking about the kind of questions that I could ask, if I had you write some pseudocode for that, you're gonna have the actual code. I'm assuming you're gonna have the actual code on your sheet. So I'm probably not going to have you repeat something that is on a slide. I would have you interpret that in some capacity. That could be asking questions about its runtime, about its efficiencies, about when the underlying data is going to be in its worst case or its best case. And maybe trying to add some functionality. I may be querying you with like, could you come up with reasons why this sort is inefficient? So it's tough to write a pseudocode based question that aligns perfectly with code that you have sitting in front of you, because you're just going to be copying that directly onto but that doesn't tell me anything about how well you understand it. It tells me, did you write that on your sheet? Which I'm not particularly interested in. Other questions before we go back to other sorts and kind of intuitively understanding other sorts? Sorry for those remote, I see that this is a little bit off center. So there's everything that I did for that.
Or could you just talk about why we use that recursion?
Yeah. So with recursion, we've talked about stack memory and heap memory, where we have the stack growing down and we have the heap growing up. We have what goes in heap memory? Basically structures, and with the keyword new, any data that gets passed by reference. So an array list, linked nodes, anything that has a constructor associated with it lives in the heap memory. In the stack memory, you have primitives and you have reference variables. So this is anything that becomes out of scope if you leave a method and go to another one. And this is anything that you don't have to do that to. It stays consistent. So if you make modifications, if you pass an array by reference, and then you make a modification to that array, when you go back to the original scope, it's still changed. And the reason is, like, let's say we make an array to sort. And then in some function, we make a reference variable with the associated name. So this would be like the ARR for an array that points at this structure. It just tells us where this structure is in the heap memory. These are very small, these can be very large. We have a lot of this, we don't have very much of this. When we make a new function, we are going to be adding to our stack memory, because any local variables to that use what we call a stack frame. So we make some amount of space in the stack memory. Let me throw this back over here. We make a stack frame. And maybe this is our merge sort with a list of size 32. Then in merge sort with our list of 32, we're going to make a recursive call to a merge sort of size 16. When we do this, we still are using our original array, but we're duplicating the name for it. So in here, we have some variable called ARR that points here. In this, we have some variable called ARR that points here to the same structure. But we're duplicating our stack frame and we're duplicating our variable names because they're called the same thing. But any local variable we make in a recursive call gets duplicated, as well as other things about the other things that get stored in this is like the line that we're currently on. When we return from a recursion, we go back to the line that we were on when we left. So we need to store that somehow. When merge sort 32 calls merge sort 16, it'll keep track of we were on line 16 when we left. So when we return, we're going to come back to line 17 or the next instruction. So all of this takes space. You can imagine if we had a giant merge sort that we would have stack frame after 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 stack frame. This is also what you see if we have an infinite recursion that recurses and doesn't get closer to a base case. We just continue to recurse, continue to recurse, continue to recurse. We get a stack overflow exception if we run out of this memory. So the entire purpose of tail recursion is to avoid this issue. And a tail recursive call says that once we finish this process, there's nowhere to come back to because this work is done. If this work is done, we can get rid of this out of the stack memory and free up that memory. So when we call this procedure, we don't need to go back to this procedure. When we finish this procedure and call the next one, we're done with this and we don't need to go back to it. And the reason this is useful is that anything that we could write recursively, we can also write tail recursively. This is not super important in Java because Java doesn't actually support tail recursion. But it's a very important concept in functional languages and other languages that support the functional paradigm. Because iteration doesn't exist in those languages. You can use while, but underneath the hood, what while is doing is recursion. So you need to think about how to do this. So I just introduce the concept of tail recursion so that you know what it is. It's just one of those things that I may ask you to describe in some capacity. I'm not going to have you write a tail recursive solution to something. I only gave you one example of that in slides. It's not a huge outcome from this course, but wherever possible, I just like to sprinkle in some more advanced topics just so that you know what they are. And that way, if you ever run across them, you have seen at least some intuition behind what it is. So writing recursive functions in a way that you cannot get a stack overflow exception because we free the stack frame when we're done with the recursive call, rather than putting it on hold and waiting to come back to it in the recursive chain. Any other points from the study guide? Yeah, so all stack functions are constant, and that's by necessity. Otherwise, we would just use a list. Lists have everything either constant or linear. And a stack is a restriction on a list such that everything we do to it must be constant. And that says for problems that we can solve with just a stack, now we have a guarantee that on a per operation basis, we have constant time for everything. And that's very useful. I mean, we've solved some stack problems, for instance, with postfix. And you can imagine implementing this with a list rather than a stack. If instead you were putting things at the beginning of the list instead of the end of the list, you would end up with linear time operations for everything rather than constant time operations. So rather than even allowing that, we just have this stack structure that guarantees that we're going to be able to do everything in constant time. The entire design of the stack is to be a constant time structure on a per operation basis. Same thing with a queue. You want a constant time structure. More restrictive than a list, less powerful than a list, but solves the problems that it can solve more efficiently. Guarantees that efficiency. All right, we can go back to one more sort, I think. We have just enough time for one more sort. We have a preference for selection sort or bubble sort. And we looked at an average case. Do we want to do a worst case, a best case, another average case?
Bubble worst case.
Bubble worst case, let's do it. All right, so in bubble sort, we start in a completely random order. We don't know what any of these are. And the goal is to just continuously make passes through the entire structure. And whenever we see something that is out of order with proportion to the thing that is next to it, we're going to just swap them. So we start by looking at, we always start looking here, and we're going to ask, are you out of order? If so, swap it. Are you out of order? If so, swap it. Are you out of order? If so, swap it. Are you out of order? If so, swap it. After this process, we know that the largest value is in the final slot. Because wherever it was going to be out of order with everything that was after it. If this is the largest element, we're going to need to make this swap. And then this swap, and then this swap, and then this swap. Otherwise, somewhere along this path, we're going to be discovering the largest element. And we're going to bubble it all the way to the end. During this process, let's say the smallest element was right here. Where is the smallest element after this first outer loop pass that gets the largest element to here? It's one place closer to where it needs to be. It's going to be back here. So with one pass, we are not done. With each pass, we're going to get each element one place closer to where it needs to be. Except for the largest element, or the largest elements, which are going to be moving significantly closer to the end. So we're going to be taking large elements, moving them closer to here, smaller elements, slowly bubbling them back. The reason it's called bubble is to remind you a lot of something like, I don't know, kind of the way that oil and water, if they're perfectly mixed, kind of slowly shift apart. The extremes become apparent quickly, and then everything else becomes apparent a little bit less quickly. So we're doing the, first of all, how many outer loops are we doing? In the worst case. We're doing this process, how many times? N-1 is the absolute worst case. Because if the smallest element is right here, it's gonna be moving back 1 time per time that we're doing this. So after 1 pass, the smallest element is here, 2 passes, 3 passes, 4 passes, and now we're done. Now the entire list should be sorted. So the outer loop would run at most N-1 times. In the worst case, how many swaps are we making and comparisons are we making each time through this? The first time is gonna be N-1. The next time, how many times do we need to do this? N-2. Since we're doing this sequentially, this is an addition. And then we're gonna be doing this N-3. So really, if we wanted to say that this is the worst case, we know N-1 is the worst case. So we can just kind of get rid of the rest of this and just say, you know, what if this was just N-1 times every single time? Really, it's about half of that on average, but now we just straight multiply the outer loop times the inner loop, N-1 times, we're gonna do some amount of work that's either N-1 or less. So we do that multiply. What is N-1 times N-1? First, outside, inside, last. We have an expression now where we have a constant and a lower order and a lower order, so we get. Since I made an assumption that there was maybe some less work to do than this, we're gonna use big O here that says maybe it's in a better order because I didn't prove it. I could have gone through the work to prove it. But it is actually N squared. That is kind of a worst case upper bound of how long this algorithm could take to run. And if we were to describe this in English, I just talked about what is the process of the outer loop? What is the process of the inner loop? For each time from the outer loop, we're doing the inner loop. So we multiply because we have a loop inside of a loop. Does that help? Does that make more intuitive sense? All right, I will have office hours for the next hour for anyone who has individual questions or wants to go over anything else in preparation for tomorrow. Yes, if you are free at 11, that would be great, because I would be free.
Someone more.
If you are free at 11, if not, I can work around your schedule. Perfect. All right, I will see you tomorrow at 11. Thanks, Chris.
This week because of Pizza.